So our second mini course is by Brian Collier from the University of California at Riverside, and he's going to tell us about Higgs bundles and isomonodromy and maybe minimal surfaces. So over to you, Brian.
Great. So thank you for the introduction and invitation, Pranav. It's great to be here. Thanks to Rui for giving me such a good introduction and motivation for some of the things that will be useful for my talk too. All right, so there's a title. Everything I'm going to say that's new is going to be based on some recent joint work with Jeremy Toulis and Richard Wentworth. I'm going to start by just giving an outline of the types of things I'm going to talk about. So I'll start by kind of setting up things and giving an overview. And then I'm going to spend a good amount of time talking about what I'll call structures on the configuration space. This will be, like, I don't know, a lot more down to earth and lots of details. And then I'll talk about something called we're calling the joint moduli space. And then I'll hopefully tell you about a stratification of it. And its relation with these, what I'll call isomonodromy. Isomonodromy. And then in the end, if in the like probably negative 30 minutes I'll tell you about applications for normal surfaces. Okay, at least in the overview, I'll mention some of these kind of aspects, but I don't think we'll get to any of those details. We'll see. Okay, great. So let me fix some kind of mathematical objects to start. So main players. So sigma is going to be a connected oriented topological surface, and its genus is going to be at least 2. And associated to this topological surface, there's going to be an important space called the Teichmüller space of sigma. So this is a space which parameterizes ways in making my topological surface into a complex manifold. Okay, so just as I said, it's going to be all complex structures on sigma, which is a big infinite dimensional space, up to some notion of equivalence, and that notion of equivalence is acting by the identity component of the diffeomorphism group of sigma. Okay, so that's so G is going to be a complex semi-simple Lie group. So I really wish I would have stuck in with vector bundles, but somehow one of the main features of what I like about this work is how natural things appear on these principal bundle things. So, but mostly, if this makes you a little nervous, you should think of the Lie group SLNC, and everything will be about vector bundles. Okay, so associated to these two objects is one of the main important spaces. So I'll call this XG. Okay, so this is going to be sitting inside what's called the G character variety. So these are all just representations of the fundamental group or group homomorphisms from the fundamental group of my surface into the Lie group G, considered up to conjugation. So this space is usually called the character variety. And today, or not today, whatever, in the next 3 days, I want to focus on the set of stable points of this character variety. Okay, so this is going to be the smooth or orbifold locus. So this is going to be the set of equivalence classes of representations of the fundamental group such that rho is irreducible up to conjugation by irreducible, if you should think about SLNC, is that it's irreducible, no invariant subspaces, or in general, if it means that the representation doesn't factor through a proper parabola. Okay, so the thing I want to care about is some extra structures like metric structures or symplectic-like structures, and we're going to focus on the smooth locus of these things to talk about. Okay, so that's one of the restrictions. One of the nice features of this space is it has a natural complex symplectic form, which is called the Atiyah-Goldman form. So this is a holomorphic symplectic form on the character, on this space XG. Okay, so great. So what are Higgs bundles all about? Well, they kind of sit in this Kobayashi-Hitchin type correspondence with, okay, let me just say it. So there's this theorem, which I'll just say for this intro part, the non-abelian Hodge. Says the following. So this space just cares about the topological structure on my surface, just its genus, its fundamental group. And the theorem says that if I enhance it, my topological surface into a Riemann surface, a complex manifold, then there is a real analytic isomorphism which I'll call Hx from some other space, which will be called Mx, to this character variety. Okay, so what's this space? This is this moduli space of Higgs bundles. On my Riemann surface. Okay, so just to give you a feeling for what the objects are, so let's just set G to be SLNC so I can work with vector bundles. The objects here are pairs E phi, where just like in Rui's talk, E is going to be a holomorphic vector bundle. We're going to assume its determinant is trivial. And phi, this is some additional thing, some additional data, more than just your holomorphic bundle. It's going to be a 1-0 form valued in the endomorphisms of E. And it's going to satisfy the condition that it's compatible with that holomorphic structure. Okay, namely, it's holomorphic. Okay, and then there's this. Because it's some moduli space, and as Rui kind of motivated, we're going to assume it's going to be stable. Okay, up to some notion, natural notion of. Okay, so in particular, the objects are maybe one, you need the Riemann surface to define them. Then what? Oh, this is the complex structure. Okay, so. Okay, maybe I'm getting ahead of this. So X is just a Riemann surface, but its underlying topological surface is sigma. Okay, any other questions? Okay, cool. Great. Okay, so some nice features of this Higgs bundle moduli space over my fixed Riemann surface is that it's also a holomorphic symplectic orbifold. For SLNC, there's no orbifold points. But one of the kind of things you might, as we're talking about scalar metrics as being important, subject. So each one of these spaces, this one and this one, have these holomorphic symplectic structures. And maybe each one of them by themselves, if they didn't know about the other, isn't naturally a Kähler manifold. Okay, but one of the amazing features is that if I define omega x to be a pullback by this identification of the real part of the Itzia-Goldman form, this real part of this complex symplectic form here, this is a Kähler form on MXG. Okay, so this is somehow the objects that we're going to be talking about. Okay, so any questions? Yeah. Good. Okay, so since I'm on a one-dimensional complex manifold, I don't need an integrability condition. So the question was, why don't I have an integrability condition on the Higgs field? And it's because I'm on a one-dimensional complex manifold where there are no 2-0 forms. So it's automatically satisfied. So yeah, everything can be, not that I'm going to talk about, but in this part of the story can be said for compact Kähler manifolds, and my compact Kähler manifolds will be one-dimensional. Okay, great. So let me tell you about some ingredients. Well, maybe not. Okay, so let me kind of navigate over here and ask some kind of motivating questions. For me. Okay, so this is I've been thinking about these spaces for a while. A question I've always really wanted to understand is the following. So given a representation of the fundamental group, how does the associated Higgs bundle, so this holomorphic object I've built on a Riemann surface associated to my representation, depend on the choice of x? Namely the Riemann surface. And that's, of course, a question. Okay, so maybe here's a more specific, so that's a very vague question, which makes it easy to ask, but hard to answer. So maybe just give you an example of a more specific question. So do there exist representations so that the associated Higgs bundle varies holomorphically? With respect to the choice of x.
So Ben, maybe you already said this, but can you just explain that notation?
Which
omega
one?
x, for little omega x? What's on the right-hand side?
Okay, so this is the Itzia-Goldman form, this one. So this is this symplectic, holomorphic symplectic form on the character variety. And what this means, I'll take its real part and I'll pull it back by this map. Okay, and so this map is not a complex map. It's not a holomorphic symplectic map. So I can pull back this real part of the Itzia-Goldman and get a new symplectic form here. And it turns out that that one is compatible with the complex structure. Whereas a holomorphic thing is a 2-0 thing, and this statement is at least it's 1-1. Okay. Those- Yeah. No, we'll get to a more precise statement of that exactly in this overview. Okay, and then maybe, so another more precise question, is just the part I skipped, was about these minimal surfaces. And so if you want to know more about that, you gotta ask me some other time. And maybe the second question that I've always been quite interested in is, so given an interesting, in quotes, subvariety of this Higgs bundle moduli space, is pushing it over by this non-abelian Hodge map, getting this thing in the character variety, independent of the Riemanns, of X. So are there examples of some, or if I choose one, which is my favorite, can I understand how the image changes as I change my Riemann surface? Okay, so these are the kind of motivating questions. Let me tell you about two theorems I want to tell you about. One is a construction of some moduli space, which is a bit bigger than mx. And the other, as kind of Rui motivated, is some of the extra structures you see from an analytic construction of it. Okay, so to answer kind of these questions and more specific versions of them, it would, to me, as a differential geometer, be very natural to have a big moduli space, one where you're kind of has the variation of the Riemann surface built into it. Okay, and the first thing I'm going to kind of hopefully tell you a bit about is a theorem which is a construction of that. I guess I erased, oh, there. Okay, I'll write it once and then stop writing. Okay, so there is a complex orbifold Mg with no x. Where am I? Sorry. Touch that. One, it fibers over Teichmüller space, this space that parameterizes all different ways of making my surface into a Riemann surface holomorphically. And the fibers are biholomorphic to my moduli space for my fixed Riemann surface. So this is the type, this says at least it's the type of space that I wanted to have. Some other features of it is, one of the nice features, I should say, of the character variety, which the Higgs bundle space doesn't have, is that the mapping class group of the surface acts naturally here. Okay, and when I choose this Riemann surface, I kind of break that mapping class group symmetry. This space for a fixed choice of Riemann surface doesn't have a natural action of the mapping class group. And so this big space, well, does. And it acts holomorphically. And then the last thing, which is going to be important for what I want to talk about, is that this non-abelian Hodge map, this Hx, extends to a real analytic H to the character. Okay, so the the theorem is about, there's a construction of this space, and it is somehow the space I want to try to probe these types of questions. And second is that this space comes with some nice structure. So this space MG is equipped with two pieces of information. Well, okay, there's more, but I'm going to only tell you about two. The first is a closed 1-1 form, omega naught. Okay, let me call it 1, and I'll go over here with 2. And 2, a holomorphic section which I'll call capital theta. Okay, I'm going to write it down, and then I'm going to tell you how you should think of it. Okay, so let me just kind of tell you what you should think of theta. So the tangent bundle of my big space maps to the pullback of the tangent bundle of the base. And the fiber is the kernel, the derivative of the projection map, so the vertical direction. I'll call it V. Those are the tangent directions to the moduli space of fixed Riemann surface. Okay, and so theta at every point is a map like this. Okay. Okay, good. So now, so that's the first theorem that I want to try to tell you something about. And maybe part of the second part of the, the configuration space focus is all about defining that omega naught. Okay, so first remark, you notice I did not say that this thing was non-degenerate. Or I didn't say it was Kähler or something like that. It has most of the pieces, but I didn't write them there, and I didn't write them there for a reason. Okay, so from the construction, we'll see that for a non-negative number, really, there are closed 1-1 forms, which I'll call omega S. Oh, sorry, I forgot to emphasize one of the main points. So this omega naught, if I restrict it to a fiber, namely the moduli space of Higgs bundles for a fixed Riemann surface, it is the Kähler form on that moduli space of Higgs bundles for that fixed Riemann surface. Right? It is the pullback of this kind of natural thing you have on the character variety. Okay, so that was one of the main features. It's not just some arbitrary kind of new thing. It's kind of on the fiber directions, exactly what you wanted to be the Kähler. Okay, so this one also satisfies that property. And well, this is not Kähler either, but is Kähler, so and an exhaustion. On which is Kähler. Okay, so that's somehow the best we can do, or you can do. And some other remarks. So if you're an algebraic geometer, you might say, I already know of such a space. Well, more or less. Maybe you don't love Teichmüller space, but so Simpson constructed a similar space. Okay, I mean, just constructed MG algebraically. And ours is maybe analytic or gauge theoretic. And from this perspective, we, some extra information. Okay, so, and then the final remark is that you should see Luis's talk. Did I spell it right? Yeah, I definitely, I'm always confused if there's a Z there. Okay, good. I should have just been confident. In Hitchens' talk, for related constructions. So talks this week. Okay, great. So now the second theorem I'm going to tell you about is about what this extra structure is. Okay. So let me kind of set it up. So what do we have? We have this big space. It has a complex structure on it, which I'll call I. It has a projection map to Teichmüller space, which is holomorphic. And it has this map to the character variety, or the smooth locus of the character variety. And this space has this canonical, or whatever, natural symplectic. Okay, so now let me define for you two things. So first of all, what you could do, so I know for every fiber, the restriction of this map identifies with this space. Okay, so this map is not even a bijection, right? So the fibers of the map these are called the isomonodromic leaves. Okay, so what does this thing have in it? It has the information of all of the Higgs bundles, namely all the Higgs bundles on all the Riemann surfaces, which give you a fixed representation, or a fixed point over here. Okay, and now its tangent information, which is the kernel of the derivative of this map, I'll call that D, is called the isomonodromic distribution. Okay, good. So now let me define what omega naught is. Okay, so what do you want it to do? You want it, first of all, to restrict to this scalar form on the fibers. Okay, so let's see, I'm here. So one thing you might do is you would just pull back the real part of the Atiyah-Goldman form. This thing definitely restricts to the thing you want on the fibers, because that's how we, it's. But a problem is that this, it's of type 1,1 in the fiber directions, but it turns out with respect to this natural complex structure, it's not a 1,1 form. So now it's closed and it has nice properties, but it's not 1,1. Okay, so what do? You take its 1,1 part with respect to that complex structure. This is the definition of omega naught. Okay, now from this, so now this is the, so it turns out omega naught is closed, and this thing is compatible with the complex structure. Okay, now I'm going to look at the associated, Hermitian form, or thing I wanted to be the Kähler metric. Okay, so the associated Hermitian form I'll call H naught, and I'm going to use the opposite convention as Rui, or else everything, I guess everything will all be defined up to a sign anyways. So it's going to be okay, so associated to this closed 1-1 form, I'll look at the associated Hermitian form, where here I put my complex structure in the first factor, which is just a convention. Okay, good. So what do we know about H naught? H naught is positive on the fibers. Because it's the Collier metric associated to this Collier form on the fibers. Okay, but since it's positive on the fibers, that means I can take its perp. Okay, I can take the perp of the fiber directions. So I get a decomposition of my tangent bundle into the vertical space and the horizontal space, but the horizontal space is by definition the perp of the vertical space with respect to this Hermitian form. Okay, notice the Hermitian form is not going to be non-degenerate yet. Okay, great. So the second theorem is going to be about the degeneracy, is going to be about the relation between these, all these objects. Namely, you know, I've been definitely not saying that these things are non-degenerate, and the theorem is about how degenerate they are and the relation between the kernel and these other objects that I've defined. Okay, so here's, I guess there's enough room here. Yeah, I'll write it here. So theorem. Okay, so if I take a point y in MG, let's let ky be the kernel of my Hermitian form as a subspace of the tangent bundle. Okay, so this is the subspace on which H0 is degenerate. Okay, then that kernel, the space of directions on which the Hermitian form is degenerate, is equal to dy intercept I dy. Where dy, if you remember, is the isomonodromic distribution at the point. Okay, so how should you think of these? These are space of complex tangencies to that isomonodromic leaf L. And the additional thing is that it's identified with the kernel of this holomorphic section theta at the point y. Okay. So theta is not a splitting, right? It goes all the way back. It's not a connection, right? It's like the thing that connections are affine over. But any other questions? Okay. So let me kind of say something maybe moreover. Let me just write it and then I'll say what I want to say. Okay, so maybe I should saying too much, let me just write it and then I'll say what the point I really want to make. Maybe let me just say what I wanted to say instead of all of the math that's on this board. The form H naught, so I know it's positive here, and what the second part is saying is so H naught is non-positive on the horizontal distribution. Okay, so even if it is non-degenerate, it's going to be negative in these directions that are transverse to the vertical phi. Okay, so let's say, no, I don't have room. I'll state this kind of corollary, and then my overview, I guess, got a little longer and more detailed than I wanted it to be. And then we'll kind of get more maybe concrete. Okay, so let me just note the following corollary. Is that H naught, or equivalently, my closed 1,1 form omega naught, is non-degenerate at Y, if and only if this isomonodromic distribution is totally real. And the kind of second part is my isomonodromic distribution is complex, is a complex, subspace here, if and only if the isomonodromic distribution is equal to the kernel of this form. So it's as degenerate as possible at this point, and that's equal to the horizontal distribution. Okay. And maybe just to say, to kind of bring it back to Joachen's question, so I wanted to avoid mentioning theta at the beginning, but I wanted to say it just so I could emphasize this point. So you get a stratification of this space where the different stratum are labeled by the dimension of degeneracy. So MD. And to go back to Joachen's question, so M0 is where it's non-degenerate. And then the smallest it can be is 3G minus 3, is it's, this is maximally degenerate. And this question about finding representations whose Higgs bundles vary holomorphically is asking for holomorphic leaves, which are contained in this stratum, which is the closed stratum, where it's maximally degenerate. Okay. Any questions before we get into this is supposed to be the overview. Now hopefully get more concrete, and my kind of goal is to explain to you in some detail why you get something that is pseudo-Hermitian and not actually Hermitian on this when the thing is non-degenerate. Okay? Okay. Okay, great. So this is part 2 of the configuration space. And one of the main thing I want to kind of convince for the course at least is, basically I want to define how the complex structure omega naught, H naught, and theta are defined in some infinite dimensional space. And the point, which I won't be able to go into the details of, is how they descend to this moduli space, which is the quotient. Okay, and you kind of see from the construction that you just have a minus sign in a certain place that is just there. Okay, good. And it comes exactly from varying the Riemann surface. Okay, so here's what I'm going to. So now let's fix a C infinity principal G bundle. P over sigma. So this is some manifold. It has a free action of G on the right, such that the quotient is sigma. Okay. So this is, G was SLNC. If I could, would come to me as the frame bundle of a rank n vector bundle, which had a volume form on it. Okay, great. And denote by VP the subbundle of the tangent bundle, which is the vertical bundle. Okay, so as a set, my moduli space is going to be some big space, which I'll define for you, of stable Higgs bundles on P mod some group, which is called aught P. Okay, and it's going to map, kind of before I quotient, map down to all complex structures on my surface. And the resulting action of this group on the quotient will be, on the projected down, will be of the diffeomorphism. Okay, and so this is how you will build this thing over Teichmüller space. Okay, so I will define this, but let me first define this group for you. So aught P, usually when you do Higgs bundles or just bundles on a Riemann surface, or a Kähler manifold or whatever, the group, which is the thing you quotient by, is the gauge group. Okay, and the gauge group, most importantly, covers the identity on the surface. Okay, so this is just a slight enhancement. It's going to be all bundle automorphisms, they would project down to diffeomorphisms, and I only want the pieces which covers the identity component. And the fiber, the thing that covers the identity, is the group you usually quotient by, which is called the gauge group. Okay, so this is the kind of natural group that is arising here. Okay, and I already said it, but the idea I want to convey is I want to kind of tell you about how all these objects are on a big configuration space to kind of, well, I think that's the best I'll be able to do. And I think you get a lot of information from understanding, how they kind of are canonically or easily defined on this space. Okay, so just like in Rui's talk, how do you, this is my kind of naked complex vector bundle, no holomorphic structure. And I want to kind of build a space that has all the data of all the different ways of making this smooth bundle into a holomorphic. Okay, so usually I use vector bundles and think about d-bar operators. Yeah.
I want to ask, are there any restrictions on the type of G you're looking at?
G is semi-simple for this talk. I think you can make it work to be reductive, but yeah, the story is kind of rich enough here that you can add more adjectives, and I think things should work out. Some of the things would be a little more technical or difficult, but we kind of want to focus on the other structures. Okay, good. So what are holomorphic structures on P? I asked Oscar if Ramanujan was here, and question was mostly for this point. So I learned all about this by reading certain lecture notes of Ramanujan, which I guess he wrote from lectures Kozul gave when he was a PhD student or something. And anyways, they're kind of a very nice set of notes. They are available on the internet if you look hard enough. Okay, so holomorphic structures. So this is going to be the space JP. I'm going to define it for you, but let me first kind of tell you an important point. It has a natural map to the space of of complex structures on the surface. Okay, so a complex structure on my principal bundle will have some sort of forgetful map, which induces a complex structure on the base. Okay, so what are these things? Well, first of all, they have to be complex structures on P as a smooth manifold. So they're J's. Okay, so here's my definition of section, so this is Ruiz notation. So they're sections of endomorphisms of the tangent bundle such that, well, they square to be minus the identity. So they give me a complex structure on all the fibers. And kind of the way I want it to be, kind of remember the principal bundle structure is I want them to be G equivariant. And most importantly, the fibers of my G bundle are G torsors. Okay, so their tangent space, they already have kind of a natural complex structure coming from the group. And I want it so that when I restrict that to that complex structure to the fiber, it's the one on the tangent space of G, Lie algebra. Okay, so what does that say? How do I write that? I say J of X sharp. So on the vector field induced, okay, let me just write it first. Okay, and the complex structure in the Lie algebra, of course, is multiplication by I. Okay, so this is for all X in G. Okay, so this says the way it acts on a vertical tangent vector is it acts by multiplication by I. Okay, so this is the space of almost complex structures on the principal bundle, and since I'm on a Riemann surface, this is higher dimensional, but I may not go into it. But the property of these extra restrictions and the base being one-dimensional as a complex manifold implies that these things are automatically integrable. Okay, so this is actually the space of complex structure. Okay, great. So what is its tangent space? Are there any questions on how you're going to think about it? So let me say this before it comes up. When you think about the space as complex structures instead of analogous to like Dolbeau operators, these D-bar operators, many factors of 1/2i pop up. And that is the explanation, as we may see, of why these extra annoying factors of 1/2i will show up. They haven't shown up yet, but nevertheless, I feel like, I don't know, setting it up in this language, I felt like it was rather clean. Okay, good. So our objects are, our symplectic forms or things like symplectic forms and our Hermitian forms are going to be defined on the tangent space of these things. So we need to understand the tangent bundle. So what are these things? Well, I just need to differentiate these conditions. Okay, so they're M's in sections of endomorphisms of the tangent bundle. Well, they have to be G equivariant again, and I'll start calling, just putting an upper G to insist that they're equivariant. Now, what do you get when you differentiate this condition? This condition, this differentiates to say Jm plus Mj is 0. And the second condition says that it's fixed on the fibers, and when I differentiate something that's constant, I get 0. So when I restrict M to the vertical bundle, it vanishes. Okay, great. Okay, and so another important set of objects are going to be, okay, so let me write it like this. So these are analogous to one forms valued in the endomorphism bundle of a vector bundle. So this is called the adjoint bundle. So G acts on its Lie algebra by conjugation. So I can take the product of P with G, and I can quotient, so it also acts on P. I can quotient by the diagonal action, as long as I make a right action into a left action, and get a Lie algebra bundle over my Riemann surface, or over my topological surface. Okay, so that's a good important thing. These are what you think of in terms of vector bundle. I say one form's valued in endomorphism. Okay, but in terms of this principal bundle story, it's more natural, or it's equivalent, let me just say like that, to think of these as psi's, which are sections of Hom from the tangent bundle to the vertical bundle that are G equivariant more and satisfy the property that they vanish on the vertical bundle. Okay, so being equivariant valued in the vertical bundle and vanishing on the vertical bundle is the condition you need for it to descend to something on the surface. And when you do, you get a section of this vector bundle. Okay. Now let me define, so I was telling you that the moduli space is going to be this quotient of this infinite dimensional space by this big group. Let me tell you what that space is. Okay, great. So Higgs on P is the space we're after, and it's going to sit inside a bigger space, which I'll call C, and this thing is going to sit inside just a product of all complex structures across all sections of this adjoint bundle, or sorry, one form's valued in this adjoint bundle. Okay, and I'm going to be thinking of them like this for most of the time, but writing this because it's a nice whatever thing. Okay, so we know what this is. We already defined it. What is C? Didn't leave enough space. So C, well, it's pairs J, what am I calling it? Phi. Such that, well, phi, and if it lived over here, it's any one form, right? And so I want a condition on it that it's a 1-0 form with respect to J. Okay, and here I really want to think of it like this. I'm going to precompose on here by J. So this just says that phi is a 1-0 form. Okay, and then what are Higgs bundles? So remember when I defined the kind of Higgs bundles in terms of vector bundles at the beginning, they were pairs which were a vector bundle, 1-0 form valued in endomorphisms of that bundle, almost there, plus a compatibility condition. Okay, so this space, which I didn't leave enough room, it's the set of J phi in C such that d bar j of phi is 0. Okay, so this is the condition upstairs. That was that. And now that was 55? Okay, good, good. Okay, so now at least let me define the complex structure on this configuration space. So what is the complex structure? Well, first of all, on JP cross okay, so the way thing it is going to be naturally defined on this product, easy, and each one of these things will be a holomorphic subnet. Okay, so remember here a tangent vector is an M, which satisfies these conditions, where this is a plus and not a mix between them. And theta, well, this is already a vector space. You know, it's its own tangent space. Okay, so what is I on this? It's Jm, J theta. I'm going to post-compose my endomorphism by J. So this is, sorry, complex structure at J phi. Okay, so it depends on the point you're at. Okay, and so indeed, right, you're going to see that it's a tangent condition, tangent vector by that. Of course, you notice it squares to minus the identity, and since these objects are valued in the vertical bundle, and the complex structure on the fibers is just multiplication by I, you know, and I'm post-composing, this is just Jm I theta. Okay, so now let me kind of end by let's just write down what the tangent space to the configuration space C is. So what is T at a J phi of C? Well, it's a set of M thetas, same as before, but they have to satisfy some equation, which is comes from differentiating this condition. Okay, and what do you get when you differentiate that condition? Remember, theta is like the piece of the derivative in the phi variable, and m is the piece of the derivative in the j variable. Okay, so when I differentiate that, I get theta composed m, theta composed j, plus phi composed m is equal to I times theta. Okay, so this is supposed to be a small theta, but I didn't anticipate having to write so big. Okay, so what does this condition say? Here's your first factor of 1 over 2i. It says that phi composed m is equal to, well, sorry, 1 over 2i times phi. Maybe I should just write it the other side first. 2i times the 0, 1 part of theta with respect to j. Okay, so these, you know, when you have a fixed Riemann surface, all of your things, you know, you don't vary the Riemann surface at all. The tangent spaces to 1, 0 forms is 1, 0 forms. But here you see that when I'm varying my Riemann surface, the tangent condition, you know, picks up on the Higgs field piece, this phi piece, has a 0, 1 part in its, you know, in the definition. Okay, so let me now erase it and put 1 over 2i there. And then I'll finally note to end that this is only going to depend on not really m, but the image when I push M down to a tangent vector on Teichmüller space. And that's exactly because phi lives here, and it vanishes on vertical things. The vertical piece of M will not be seen when I do phi composed. Okay, so I'll pick up next time and kind of talk more about how you define omega naught and this H naught and what they really are in terms of some natural L2 inner products on this big configuration space.
Questions, comments?
I guess, thanks for the talk. I guess you didn't get to the definition, but the map theta, do you have like a geometric interpretation in terms of, say, harmonic maps?
In terms of harmonic maps, no.
Okay.
Okay, I mean, kind of, I guess. So what is theta? It should be related to how the Hopf differential varies, how the Hopf differential of your harmonic map varies as you move along an isomonodromic leaf.
Okay.
I'll talk to you more about it. But that is, so it's related to, how the quadratic part of the Hitchin map varies as you move your Riemann surface.
Okay, we'll talk later. Thank you.
So this question about when is the isomonodromic leaf complex? I mean, does that have a history? I mean, is there a particular problem in the past which reveals this as an issue?
Surely the answer is yes. If Carlos was here, he'd be the person to ask for sure. So I mean, I think part of the main interest, I think all of the known examples, modulo something in genus 2, happen to be all C-star fixed points. So they come from actual complex variations of Hodge structure. If you have an actual variation of Hodge structure, coming from varying the Hodge structure, you would want to ask, what are there very special ones where no matter what Riemann surface structure you picked, you're always a variation of Hodge structure. And so this has been a question people have been trying to understand some bits about. And I think theta is more this theta, the big theta, is related to what Simpson calls the non-abelian Kodaira-Spencer map. And so it being 0 means kind of in all kind of directions, push in this your isomonodromic, along the isomonodromic leaf, you'll kind of remain how you are. So you have C-star fixed point in the main.
So I guess you already answered, but I was just curious about the motivating questions you had. So, I mean, does this give some partial answers that you would like to highlight, or?
Well, okay. One of the things that so I posed it, when is it holomorphic? I guess I never really had thought about it until I was thinking about this project, but I would note, I guess I should have read some of Simpson's papers more than I have, I guess. But I didn't understand how I would even make that statement. And so one of the things that I like about this is that I understand now kind of the type of thing I would need to prove that thing for me. That this isomonodromic leaf always has this, the state is always 0 along it or something like that. Maybe another type of question is, when are the isomonodromic leaves always contained here? In that case, it turns out they're always real because of this other condition, and they also are symplectics of manifolds. Okay, and so some of the things that we can prove are that like all these component Higgs bundles in higher Teichmüller spaces, theta positive representations, they have isomonodromic leaves that are contained in this M0. And so there seems to be some sort of dynamical big difference between isomonodromic leaves in here. They have this and also of like dynamics, at least the examples we know. And one of the things you can prove about isomonodromic leaves in here is they behave a lot like compact representations. They're these like totally elliptic representations. The image of every simple closed curve has 0 translation length on the symmetric. There's a lot more to do that I'm not trying to say I know how to do it all, but I think there's a lot of stuff to figure out still.
So this stratification, this has some natural C star action.
Yeah.
So is it somehow related to BB decomposition also somewhat?
Kind of, yeah. So this, I haven't told you a condition of being in the kernel, but it turns out this stratification is C star invariant. Sometimes, and you have some sort of, lower upper semi-continuity and taking limits, you can always get more degenerate in the limit. Yeah, so it has some interaction with this Białowieżnicki-Birula stratification of the moduli space, but it's a lot coarser because here, I guess I should have mentioned, but this map goes from like the tangent bundle of Teichmüller space in. So it's the maximum this D can be is 3G minus 3, no matter how big the rank of the group is. But in rank 2 for SL2, you can really write down pretty explicitly what these MD are. They're related to these Dth critical loci of the kitchen.
The questions? I have a quick question. So this omega 0 gives you a presymplectic form on this MG, right? Is there do you expect some natural description of the associated symplectic space when you quotient out by the perpendicular to the symplectic form?
I don't know. I haven't thought about it. On M0, at least it's already symplectic. I mean, the point is that, I don't really know how the presymplectic, I don't know the story very well, but, the rank, anyways, the stratification is about, how degenerate it is.
Yeah.
Generically, it is non-degenerate.
Yeah.
So, I guess generically you have this nice, not Kähler, but pseudo-Kähler structure. But I haven't thought about any quotient.
Question there, and then we can.
Is omega not related to the Weil-Petersson symplectic form?
Good question. No, but omega S is. Is omega S on the board still? Okay, so the problem is, maybe just say this quickly. Okay, so when you want to construct some moduli space, so I want to construct some moduli space and prove some slice theorem for the action of this group. And you really want to have a metric of something you can take L2 inner products with. So you Sobolev complete your Fréchet manifold, and then you talk about harmonic tangent vectors and model your slice on the harmonic. Okay, for that whole story, of course, you need something non-degenerate and positive. Okay, so this H naught isn't the thing, almost always. Okay, so but to do the construction, that's kind of the role of this omega S. So how do you compensate for this minus sign? I think this will become clear, hopefully, at the end. You can add a large enough value, S times the pullback of the Weil-Petersson form. And that will kind of, if for S large, for any point, there'll be an S large enough so that this thing is positive. And a miracle happens that the harmonics you're going to build with respect to HS turn out to be independent of this parameter S. That's somehow one of the technical things that are proven that make everything pretty nice. I guess the main point is that it doesn't require choosing like a conformal metric on your surface at all, which defining Weil-Petersson does.
If there are no further questions, let's thank Brian again.